then yeah.
Dear colleagues, today's speaker is Hrachya Babujian from Yerevan Physics.
Yes.
Given us about formfactors, formfactors.
Yes. Yeah. Thank you. Thank you very much to have a possibility to give a talk here in IMSA. The subject of my talk today is the asymptotic factorization of the exact four-factor in one-dimensional integrable quantum field theories. Especially, we check the asymptotically free quantum field theories because we want to investigate this. But before to start my talk, I want to little bit for the, especially for young, because they don't know about the four-factor program. I will give you some little bit some short review. What is the four-factor program? So in middle of something 40s, Werner Heisenberg proposed alternative way to something move to in science, in theoretical physics. Because already in 40s, after 60s, and especially after work of Landau, of course, of Kalatikov, was some people disappointed about quantum field. So this is correct way we're doing the so infinity things. This, I mean, charge is not so correctly defined. Yes, something after this work, almost. And then Heisenberg saying, you see, what is the experiment we have? Experiment we measure crossing section. Why we need to have such a macroscopic theory complicated with such big problems? Let's just start immediately, write some equation, or discuss the analytical behavior amplitudes. Yes. So then really they start to do in four dimensions. Yes, this is famous work of Cho. Then starting Hrachya, Gribov, and so they did this long time. This until the 73. 73 after the discovery of asymptotic field, this start slowly to change to the microscopical field theory, because already was chance people can see the chance that this is possible to describe something strong interaction, because the interaction could be different. Yes, when you particles are close to each other, they don't feel each other. The opposite, they're going sides of proton, then they have strong interactions, opposite of the which we have in quantum dynamics. So, this analytical method, the dispersion relation they call usually, this slowly died something in the 70s, yes, something, and then disappear almost. But now sometimes they just remember this analytical behavior of the amplitudes. But in two dimension, this was completely different. 1 + 1, yes, because we have Yang-Baxter equation, and this complete change. We have exact particle matrix. This completely changed the life. Yes. So this the Heisenberg idea, what was to use just S matrix to reconstruct quantum theories, because in experiment you have measuring only S matrix. So now in this the program, which I am four-factor program, was started in Chernogalov, Polakov ideas, and in his student Vergiles Grianek first paper. Then immediately there was a lot of papers very fast. The Ring group, Sasha Zamolochikov, and so on, many other people. But first, as program formulated in Berlin. Yes. Finally, Smirnov something. So, in this program, quantum field theory, one plus one dimension, one can construct in 3 steps. 3 steps just. First step. In first step, the S matrix. Yes. So we get the S matrix, calculate S matrix as solution of the Yang-Baxter equation. First, crossing symmetry. and unitarity. And fourth, maybe also some additional assumption of maximal analyticity. It means that poles which has S matrix should be motivated physically, because always you can have poles which are not physically motivated. This is called CDD poles. Then you should really something. And this reason is first step. People did a lot of work. Each time they're getting solution of Young-Baxter equation. Yes. So Young-Baxter equation here. How they did. Integral, of course. I speak only integrable models. First part was Heisenberg ideas, but this idea get only the good application for in the integrable quantum theories one plus one dimension. And in four dimension, this died. Only some pieces of course, still in the life, not using connected with string and so on. Yes, so physical poles should be how they did. The Skarovsky, Zamolodchik, all these people, also in Leningrad, people did also Arefeva, Kulish, they compare quantum field theory. They did perturbation theory, Lagrange, yes. Then compare some expansion of exactness methods. They get agreement. You should compare, understand what is the connection between the S matrix, which you get from Young-Baxter, which is completely nothing to do with the Lagrangian, right? So in this way, they make a bridge between the S matrix and the quantum theory. This was the first step. So this first step. So second step. Second step is the calculation of the four factors. So calculation of four factors, what is the four factors? Four factors is some complicated matrix elements of the oh. Yes. Such a if OX is a local operator, then the four factors we call such a O vector or more, so more. This equation in Berlin, something some for 2-3 points and n point, but that was I think not full. And finally, which equation I will write this was formulated by Fyodor Smirnov. And this is his birthday. He did a great job and formulated this fantastic equation, something 5 equation. I will write later. Yes. So this is third. This is I will call the Weiss-Skarovsky-Smirnov equations. Yes, these four factors are a solution of these 5 equations of the Weiss-Skarovsky-Smirnov equation. And third step is the final step. If then we have these 4 factors, then we can calculate also the correlation function, Weidmann functions. Yes, Weidmann functions. So it means we can put for example, x is 0. Here we put complete set, then we get n equals 0, infinity. So then we have 2-point function. Yes, you insert here just one, yes, for example. Here's integration and summation of all statistics. Just one. So you insert there, and you get 2 points, and yes, if you want to calculate endpoints, you have to make insertion everywhere. Yes, something. Here, everywhere you put such a one, then you get endpoint white function. So, and then if you have these 3 points, this Weidmann reconstructed theorem, which is called if all Weidmann function is calculated, then quantum field theory is done. Yes. So, but of course, problem exists here, but here, this summation, here we have here. About the convergence of this, yes. All points, you can calculate all points. All points. So, but you should show that this exists a convergence of the series, it's infinite series of the all possible channels here. Yes. So this problem, of course, still until now not solved. Only 2 cases we have. This is the Ising model and the Young model, which Young-V model, which Smirnov data proved that these 2 series are okay. Experimentally, if you start to calculate to look the convergence very well, very fast, something to learn. But to prove it, still until now we don't have any proof of this problem. Yes, so still open this problem. So also I should say some words. Maybe people also forgot about you that usually exist these Weidmann axioms. Yes, so such a quantum field. So this easily satisfies the Weidmann axiom. Answer yes, it is satisfied Weidmann axiom. For example, first one, assumption of the relativistic is usually called W0, W3. Yes, so the W0. This assumption of the relativistic quantum mechanics exists. Scalar product in Hilbert field. Yes, it exists. This is no problem. In this two-dimensional theories, we have this. Well, this is the assumption of that exists set of operators which create the Fock space in Hilbert space. Yes. This also can be easily formulated in two-dimensional. W3 is the local commutativity for microscopical causality. For this reason exists famous Fedor-Smirnov theorem, which proves it's a fantastic theorem. Listen, this is further proof that if you have such a solution of 4 factors, then you have for the intervals. Yes. So local commutative theorem. Proof. So using just that, you can insert here again the one you insert between these fields and so. Beautiful proof. Of course, it proved when they are in the space, don't has any poles, but it means between the commutator between two fields is 0, then interval between x, y is space-like. Yes, is a usual causality theorem. Fedor-Smirnov proved this theorem, and it means that if you have solution, 4-factor solution you have, then one can prove that local causality theorem is also satisfied. Yes. So it means that this theory is really something, this two-dimensional theory, that some diamond in a quantum field theory, because so you can in principle calculate everything. But this problem of to prove the how to series behavior. And then this is still what, but it is a lot of now works and young persons working in this direction, and so, and this is this will be, yeah. Yeah, that's true. So this did a hard job. This is true, but this really need long-term work in this. It's not done, unfortunately. I mean, two examples we have until now, which further proposed a long time ago. So no more examples we have still until now. Yes, yes, presumably yes, everything, but how to do it? Yes. So now, so this is I briefly bring to your attention aim of the Gross and Gross four-factor program to construct all Weitkamp functions in this one-dimensional, all possible quantum field theories. Is a lot of examples. Sinus Gardon, I don't know, ON sigma model, SON sigma model, ON Gross-Neveu model, a lot of nice theories exist which belong in this series. Yes. So today, but what is the now formulation problem which I want to bring to your attention? Yes. No, this is something different. No, this is different. It's a little bit, yeah. Not unitary, exactly, yes. This is non-unitary theory, but yes. Not fully. Of course, you get some problem, yeah. Not, yeah. This is not unusual in the theory, yes. So, our most important motivation to which they will bring this is investigate high energy behavior of the four factors. So exist four factors. Yes, I would say that this you have the momenta variables. Yes, but better to move to the momenta to the into dimension where this is the more much better picture of the post structure we have. Then you have the rapidity variables. Yes, so then you have the rapidity variables, and then you have usual. Yes, it's much better. So then you can go there and post structure much easier and nicer. So and then four factors depend not momentum but rapidities. So four factors. This is the object which depends on operators, some indices, and then theta 1, theta n. So such an object, which is meromorphic functions in the whole theta plane. Yes. Yes. You can calculate. Yeah. You can calculate Ising, for example. We also did. So you can calculate all these integrals which exist there in this series. Then you can sum up this series and get the famous result for 2 points. Yeah. This I don't remember such details. No, I'm sorry, this I don't remember. But you can calculate, just you can calculate this. Yeah. Ising, for example, Ising is some interesting with some changing signs. Some say it's easy. You can calculate. You can almost all this possible in x over 1/8 to over this distances of the behavior of Ising. You can calculate exactly from this four-factor approach. You can do it. Yeah, of course, yes. It's not powerful. This is a complicated some integrals, which is some numbers. Yeah, yeah, something. You see here, you have to get something to function from the left-hand side, different from x. Yes, so you know, x is an exponent. Yes. So, but this object is so complicated, usually, very complicated. I will write the answer of the four factors if my time will be something okay. So then you will see this, because it's exact quantum field theory is calculation. This is too complicated. So my aim is to understand high energy behavior of this. I'm sorry, I forgot to tell my co-authors. So my co-authors is Mikhail Karowski from Berlin and Angela Foster from Porto Alegre from South Brazil. That's for a long time. So we want to understand high energy behavior of these core factors in the sense that we shift some k rapidities theta k to omega k plus 1 theta a, yes, and then omega goes to infinity. Yes, what comes out for the fixed operator? This alpha indices. Yes, what is this? As usual, Smirnov also investigate this point. You get a nice result. Stein-Gordon he did, and in the point SO2 symmetry. SON much complicated. This is the point. SO2, of course, easy to prove, but SON is complicated. I will not bring the proof. So this is, but why this is interesting? This is interesting from several point of view. I think that time I don't know. Hrachya gets interesting application to the current algebra, the Adler's approach and so on. He gets some nice relation to the other functions and so on, further. But we want a little more, something to get not this current, but again, some structure function in real four-dimensional QCD exists such a structure function, which is the maybe main object in the when the people start to understand QCD in this Bjorken scaling and Bjorken behavior and so on. So this we believe already in our paper, next paper already but we start in this such a behavior investigation. So answer is for that. It's very interesting. So answer it now. I will write the result. Yes. Then you ask result of this. So such a interesting formula we have. Result is following, which is general result, and so result is following. So if we have alpha, so alpha means some quantum number, spin, and so on. Yes, some all possibility. Theta omega, yes. Theta omega means first theta k theta k plus omega are shifted to omega, yes, theta k plus 1 theta a. This means so when omega goes to infinity, then this is equal to C operator k L k plus L, well, N. So times F alpha hat it here the head. It is the F anti-head. It is alpha anti-head. It is theta anti-head. So these are the results, you see. So So this is the main our result. So the problem is to calculate this constant. Yes. First, so here's for this O anti-heat and O heat is going to summation. So it means you have to calculate the right-hand side. Which kind of data is coming out even during this process of the omega go to infinity? And this constant, how to calculate it. Yes. This one, you mean? This? What in for does this limit? It means if you start to calculate, yes, solution function, then you take some Fourier transform, yes, then you want to understand how in binary of this correlation function. So it means some of the so you like in the range x or theta? Yes, so of course this is the in the range of x. This when theta go to infinity, this is a short distance behavior. Yes, this is true. Yes, when theta go to infinity, it means x something goes to something to zero. Yes, something small distance. Yeah. Space like this. Yes, this is true. Yeah. Yes. Yes. For example, x0 is good. Yes, this is true. Right? Yeah. So this is our the result, main result. Yes. So we calculate this this constants for the four operators in different case of the k and l. Yes. So this I'll bring later. So this is the main result. This is the for SO2 you can prove the Hrachya did for the Saint George, but for SON this is we don't have direct proof, but we have some very clever, some indirect proof of this relation, which is of course in SO2 gets the correct result. So we believe that it's correct. We believe in some strange way we prove it very clever, but complicated. So this is the result of this investigation. It's a long time. Now we believe that this investigation will help us to really move to the understanding of the main once more, our goal to understand such a behavior in a four-dimensional. But in two-dimensional symptotic features, which is in O3 sigma model, SON Gross-Neveu, ON Gross-Neveu, this is interesting to do such things and investigate so-called structure function. Structure function are such a functions which some current, yes, is indices. Some, for example, mu x, yes, and commutator to q mu 0, yes, so this function in different regime, yes. So this is was the beginning of the QCPs. All the structure function, you remember this famous Bjorken scaling, and so coming from the structure function. You take here some, for example, some P A, and here also some P B. You take some integral over some exponent e qx, yeah, and you will have some nice object which we investigate. We did this already. Now in progress, step we write really something intriguing things is many. But this next time I will explain. So, but now maybe I little bit I will not write the answer, but I will explain little bit some structure how these four factors looks like. Yes, and then I will bring the concrete examples of this coefficient and operator. Then you fix the local operators here, and then calculate these limits using this complicated integral representation which we have. We have some contour integral representation of the four factors. Yes. So now I will start to write the S matrix, which maybe many people would like to see what is the S matrix of the swing Gross-Neveu model. Yes. So Gross-Neveu model X matrix is the simple models. Yes. This is main result was now dimensions. So two particle S matrix. Yes. The BT11 plus CT P12. Yes, such a usual famous. This is unit matrix, and this is the permutation matrix, right? You can write down also in matrix form. So this is the matrix of the S matrix of the Gross-Neveu model. It is very rich. It has a rich whole structure, some bound state structure, so on and so on. Yes. So this is the we can define a theta equal B plus C, and then this equal to y from ground by this. You see this, or I forgot to tell you that these theories, right? They are the same, right? You see, the calculate beta function in these theories, right? This is exactly the same as in four-dimensional positivity. It means many things will be the same. Only not easy to gather out this information from these theories because it's so complicated. The exact object, yes. This is the most important. Long time already, this four factors calculated, but how to something physically understand all these most essential points? Yes. Yes. But this of course satisfies. It has a crossing symmetry, of course. Yeah, then change the particle, antiparticle. Yes, yeah, some nice properties. Yes. These, of course, crossing is complicated because unusual spin exists in the fundamental particles of the student particles. The spectrum is complicated. Is always this two-dimensional. You don't have the normal spin. You have something which is always you can change and so. So this is this B and so on. Yes, I can write down this is equal to theta minus eta, and C tilde equal to minus E eta, theta minus. This I'm writing, you see, in this reason to have such a feeling of what is this. Yes, Lagrangian of the theory. This is usually looks not complicated. Yes, this is the n fundamental fermions. E gamma E cap Ci 1 plus G square times psi equal 1 to m. Oh no. Yeah, this is something. Psi I. Right. Minus some and 5 set 5. Well, so this is the Lagrangian of of this theory. So the spin of this fundamental fermions is really unusual. It's equal 1 over 2, 1 minus 1 n. Yeah, this is something complicated. This is true. Yes, what is? No. Sorry, this will repeat. You also. Oh, good, yes. So, for the operator which we investigate, something, this is the, in this theory, yes, something which is some 4 operators we investigated this theory, right? So, yeah. This S matrix which I wrote is exact to particle S matrix of this theory. Exact, because this is checked. No, it's during the what's called this breaking of the symmetry. You have the generation of the mass in this theory. Yes, so you don't have mass exchange, but you have extra. How this called? How to call this phenomena? Yes, spontaneous generation of the mass. So you have the extra mass coming from the. No, this is not integrable. Not integrable. This is integrable. In this checked in perturbation theory, they calculate S matrix and they check with this that they compare, and this is exactly what the S matrix of this theory. Yes. So we investigate several the 4, let's say 4 operators. This is the Noether current, yes, G mu A, yes, which is first example, yes. So this is the, for this operators I will write the answer for this calculus, which I really cancel. So that I should keep it. So alpha this first. So this is usually this is the SON theory. Yes, I think this is should be some representation of the SON group. G is the vector, weight vector is for this operator is 1, 1, 1, 1, 0. Yes. So this is the second is the energy momentum test. Yes, which is it has the omega t is the 0, 0, 0 weights. This is the third one. So this is just I'm writing because to know which what omega, which omega you mean? This omega, this is the weight. It's SON group, yes. This is the weight vector. This is this is, yes, this is the weight. So you have to work because this SON invariant theory. You should say the operator which kind of weight vector has. So each time the integral representation for that exactly will be the same one corresponding. Each operator corresponding integral representation of integrations on different objects. Just because we need to have some complicated vector structure which is nested between different objects. So this is the source is a scalar fix. Yes, which has omega phi is 0. Yeah, so this and also the fourth is the psi fundamental theory fields. Yes, is possible to call because this is which has weight psi equal to 1, 0, 0, 0. Yes. Also something kind of charge. I would say the charge of the psi equal 1. Yes, charge is charge of this Q equal psi equal 1. So that was always 0. And spin of the cube psi is again these numbers 1 over 2. Yes, this is the spin. So, yeah, this is some special state. Even this one. This is some bound state of this fundamental part. Yes, something like that. Not bosonization. Some special bound state of this fundamental terms. Yes. Yeah. Yeah, this is very complicated problem. You're saying if you have some multiplied, some p psi something, yes, phi, something like that. Then what do? You have to do? You have to insert everywhere the unit and then start to calculate all things. Yes, it's complicated. Very true. Everything you can calculate. I told you. All endpoint functions for different. But many fields is different operators. What is this? So this is one operator, right? But I can put here one, here also one. Of course. But how then you can manage this? Only this way. Yeah. This will be some huge. Then you have to use some crossing symmetry and so on, because here will be the most complete problem will arise here, because we will not something like this. Here something theta 1, theta n, right? I will be here also state something. Then we have to, because this is well defined, not easy to calculate, but for this we have to using the crossing symmetry and push this state to the right. So this is extra big job. No, but we also possible we calculate such things. For the Ising model, for example, we calculate green functions. For green function applied for the Raman scattering. It's very so. This is so these many points correlation functions are so now. Yeah, but you see, it's correct. But in this theory, you have several fields. Yes, besides also sigma field you have there, which is not free. So a non-trivial cofactor it has, and then this makes something into physics. No, this is correct. Field theory is the free, but you have these fields also extra, which come from the no. Yes, no, but Ising model unit in interaction. You see, you have a psi field, you have also sigma field, you have mu field. Yes, but in this is the free, but sigma mu not. This is non-trivial interactions, and this order disorder fields, they are non-trivial. Yes, the four factors are non-trivial. For the psi, of course, is not. It's just nothing. You have some exponents and nothing. Yes, and this is free. So you see, shall I write the equation of the Peter White's, Swarovski's, Smirnov? Everybody knows these equations. Equation which should solve and get four factors. So 5 equations. Yes, something. Everybody knows this or not? Yeah, Ivan. Not even you know. You don't know. So, okay. So finally, you see, I should say that these four factors are solution of some equation. Yes, but this 5 equation is the usually we call 4-factor equation, or this is also possible to prove. We have one of our papers. We have proved this. This comes from the lazy reduction problem. So first, usually it's called Watson equation. Yes. How many minutes I have? Ivan. 10? Huh? In 10 minutes? Oh, okay. This guy should run. You see, I can something at this point, for example, only start to write the answer which I get for this constant. So the first equation, usually we call I. Yes, this is the Watson equation, and this is symmetry under permutation of the operator. Yes, Ij, theta I, theta j. Yes, if you change the same times the indices gi and theta j, theta I, then you have the S matrix theta ij. Yes, this is the how to change the four factors when you change the spaces and also the rapidity places. Same time. Yeah. Matrix. Yeah, but this is matrix. You see, this is the matrix. This is the spaces of the type. I wrote just in this. This is the number of the space. Big this object. In fact, yes. The second. So the second is the crossing relation. It means something that f theta 1 plus I pi 2 theta n equal to sometimes, yes, times some numbers. Then C11, this is the crossing symmetry matrix, equal to F theta 2 theta n, the 1 minus I pi times 1. Yes, something like that. So this is the crossing symmetry property when you some periodicity condition you have. And third, this is the when exists such a cause in a point when difference between two rapidities called I pi. This is usually called Smirnov. Smirnov pole is called annihilation pole. The rest of the theta 1, 2 we call I pi. While F 1n theta 1 theta n equal to 2I C1 2 F 0 3 n 1 minus 0 S2n S23. The fourth is the when you have some bound state theta 1 2 equal E eta. Yes. Then this is equal to F 1 2 is a new state, something then 3 and theta 1 theta n. And finally, if we have, of course, the 5, you have the relativistic quantum field, so then surely should be relativistic equivalent. It means shift for all the rapidities to the sum 1 mu, theta 2 mu, equal to exponent S mu, then the same four factors. If the operators going to the exponent S mu 0, then you're making Lorentz boost. Yes. So this is the equation which needs to solve. So solution of this equation we usually call the master equation. This is we we believe that our master formula is correct all quantum features in integrable one combination, independently of the S matrix is diagonal, non-diagonal. we have experience to write all possible theories. Yes. Especially last 20 years we spent, 20 years we spent to three theories construct the four factors. This is ON, sigma model, ON, Gross-Neveu model, SON, Gross-Neveu model. This was much more complicated problem, which was the very long work, really. Because you need to, because inside, I will write now the answer for that. You need to really construct such a complex, yes. Which one? Analytical condition. Analytical, this should be meromorphic function. No, I told you already that these four factors are meromorphic function in all contexts. When only have the simple poles. Simple poles. This is enough. Usually we don't have nothing more. Yes, of course. Yes. This is a subject. Yes. 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 No, not analytical. The different, of course, yes, but integral representation which writing exists some special function which is distinguished between different fields. Yes. 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 This is not true. This is not true. This is not true, you see. No. Yeah. Yeah. Yeah, this question is good question, yes. Of course, we don't know. Yes. Yeah. Yes. In what dimension? Two dimension or more. Right. Yes. Yes. Yeah. I don't know such a. Yeah. I don't know what you are speaking. We calculate all possible operators, infinity many conservation laws. There are no such a problem, such describing. Maybe we don't see this also possible. Yes, we don't saying that we don't have proof that it's a full, but some example exist. The Chernagaloka people using our formula. Now I will write the integral representation. I will show we call the P functions. And the of representation is usually called some deformed, I don't know what, some deformed cycles. Deformed cycles. Which these P functions describe all the space of the operators. We usually get a equation which has an infinitely many solution. Of course, the fullness of this we cannot prove. Pasha, this is true. We cannot prove it. We are not able to do that. But this space is really infinity. But how you know this? Yes. Operator is meromorphic or four factors are meromorphic. What means operator is meromorphic? Not meromorphic. What means this? How you see it? We know this exactly. Yeah, You see, local, non-local. This we know. Pasha, maybe you don't know what we did. You see, Pasha. You see. Okay, maybe I should write down the. Pasha, maybe you don't know what we did. You see, we each time we calculating form-factor, we compare to the perturbation theory from Lagrangian for the operator, and then compare the form-factor which we calculated, and then calculated in perturbation theory in Lagrangian quantum theory, and identified this process. You see, so not calculate anything that just think this is some abstract object. Not, of course. This identification in this reason we spent 20 years. 20 years we spent in this point. You see, or more 30 years. I'm sorry, 30. Yes. This is possible. This is might this is possible. Yes. No. This is so you're telling that exists other solutions which we don't know something. Yes, something like that. But in physics, you always exists such a problem. You're saying hydrodynamic you're doing. The exist solution you don't know. Of course, exists. This is a right solution which we know. We believe that is all. Let me see. You see. So let me use something, write the answer for that. Yes, yes. So general four-factor formula for four factors of the old theta equal to some constant f theta and then k alpha theta. Yes. So this f theta is the minimal four factors, which equal to f theta ij, right? And this k alpha, what is complicated something, which is the equal to theta equal to integral over dz. Yes, some contour of theta, h theta, z, and then p. So this is the answer for the solution of this equation. So this part is usually called minimal four factors. This usual solution of the 2-point Watson equation, and then comes this complicated many contour integrals. This is the beta wave function for the SUN with the spectral parameter z's and an inhomogeneous theta. Yes, Pasha. In this representation, here this p function only depend from the other things depend from the just S matrix. This big huge function h psi you construct using only just S matrix. But this for the p function you get equation which has infinity many solutions. Infinity many solutions. And in a case we give this equation, Dashkevich and somebody who were, I don't know, some Fagin maybe boy. They calculate for all possible solutions and compare conformal. And this was full. You can look this paper. It was the solution of the equation which wrote for this p function. You see, it's only this you put there, you get equation specific. Each group has own some this periodic function, some polynomial, simple polynomial, some z and theta. Yes. Might be. I don't know. I cannot prove that. I don't know. I don't know. In a language of theta, we believe that all solutions should be meromorphic. Until now, nobody get any solution, not meromorphic solutions. This, yes. Yes. So, but You can explain what physical problem is have a non-meromorphic function. Yes, but not integrable maybe. Not non-integrable. Non-integrable, okay, but it's integrable. Yes, of course. Yes, and then yes, yeah. I do, yes. So this is our honest contribution to that. If you can more, please welcome. What you can say about that? Please welcome to get other solution. Yes, about our honest work. We get only meromorphic. Yes, yes, please. Yeah, 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 yeah. Yes, yes. Not local. Yeah, yes, yeah, yes. Mm. Co-roots. Yeah, yeah. This is interesting point. What you're saying. So it means this is Prasauer. What is it? Prasauer bond. Yeah, yeah. Yeah, yes. But this is something to do with the unitary. Mm-hmm. Yeah, yeah, yeah. So yes, okay. This understand what it means. You're saying that if it exists this CDD poles, then you have the extra pole in the symmetry. This is another function, actually, right? Which is close to that because it's not different. Because just you add some integral of motion to your Lagrangian, yes, this is TD bar, right? So then change all the behavior of the field theory. So this is I don't know. So yes, yeah, yeah, yeah. Hmm. Yes, and then what you can calculate in this point? No, 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 no. Infinite test. What you can calculate? Feynman graph. Always we have a finite number of particles each Feynman graph. Yes, right. Yes. So now you're saying now four-factor program something to do with the ideological something false. Something. We should tell. No, no, no. This action. No, this action does not depend on apparatus. No, it's not correct. No. Yes. Yeah. What about conformal field? How the situation there? Pasha, what about conformal field theory? Situation is different or the same? Yes. Yes. So, Pasha, this negative, you will see the what, how we compare results from, I, you see, for example, G, yes, alpha G and theta omega. So to see the what kind of numbers coming out, you see, for example, this when is the current is minus 2 eta W. This is also maybe I get this beautiful formula for SO2, yes, of course. Theta, yes, heat and theta heat in FGA. Yes, GA, yeah, alpha heat, theta, and is F. So yes, GA, yes, GF, ABC. Yes, AD, right. Look at here. So heat anti-heat means something. The K K thetas are shifted to omega and L is not. It's K theta. So this is eta is the number this P over N. Yes. Also some, for example, this. Just as I am finishing, so let me wait. You see? Huh? Accident was this? The stop. Yeah. So let me. I will not write all. For example, to see, for example, this color, omega go to infinity. This of F alpha theta heat. This PF this is of scalar anti-heat theta anti-heat. Yes. So and so on. Such a, for example, here's one. Yes, like exponential pizza. Beautiful. You have more complicated, of course, for the tense energy, more complicated numbers coming out depending on the n and so on. So this is our result which we get. But the most important thing which we want, in conclusion, I want to say, this using we learn how to calculate this such limits. Yes, because object is really, we have this is an estimate beta ansatz wave function. Direct proof we don't have. So SO2 is not proof in you can calculate everything, but we not. So we believe that our experience to calculate such a object will help us to do more interesting objects like structured functions, which is to compare with the structured functions limits in the coordination PCB in experiment, for example. We already did this in the process of writing this paper. So some surprising that is nice. So the functions and the high energy limit of this structure function is getting to factorizing functions for the Bjorken variables in terms of variables of two. And this function should be universal function. We believe that all integrable, not integrable even, quantum features this is some nice function which you have wrote this time. This function. Yeah. What? Yeah, of course, yeah, explicit formula. Next time I will write it. Yeah. No, no, no. It's very simple. Thank you. Yeah. 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 You will wait. Now you're right. So this function, so this is complicated, of course. This is not universal, but this is universal. Huh? Hint? No. No hint. Next time. So thank you. Yeah. Yeah. Yes.